Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
Okay, so the title of the talk is going to be Networking Technologies for Real-Time Interactive Applications. And this is work that we've done over the last 4 or 5 years, and a lot of this work has been related to applications like remote desktop and video conferencing, link, and Skype type applications. So just before starting, I'll just give a background of some of the stuff I've worked on over the past 15 years. And I joined in about 97, and I joined in the media division. And in the media team, most of my work was related to codecs. So I worked on screen codec, and then audio codecs, and then audio processing technologies. And prior to moving to MSR, worked on adaptive media streaming technologies like smooth streaming. So we developed the prototype for smooth streaming. And then after joining MSR, I shifted my focus from codec development towards more in the networking technology side, and have worked a lot with teams like Remote Desktop and Link. And that's the work I'll be presenting today, is going to be on this improving the real-time interactive applications. So first of all, I just wanted to kind of clarify what are real-time interactive applications. So basically, a real-time interactive application is any application where you have you require low end-to-end delay. So things like, of course, things like file download are non-interactive, because mostly it's just throughput that matters. And of course, video conferencing and VoIP are interactive. But contrary to what many people believe, not all media applications are real-time. So video streaming like YouTube and those types of applications are actually not real-time. They do have some requirement on, by when packets should arrive, but they're not really real-time. And but some software applications are real-time, like interactive client-server applications. So the takeaway kind of is that not all multimedia applications are actually real-time, and there are actually non-multimedia applications which are also interactive in real-time. So as I said, what matters for RTC applications, it's not just the throughput, but it's also the end-to-end delay. And this is essentially the end-to-end delay between when you generate the content to when you consume it. So essentially, like in VoIP, it's the time between when you speak to when the other guy listens to it. And that's what matters a lot. So if you think of like network latency as, on the x-axis we have packet delay, and let's say network latency is on the order of 100 milliseconds, 200 milliseconds. And if you try to plot, quality versus, network latency, then, for video conferencing, essentially, if you have more than like 250 milliseconds of latency, then you get very poor performance. Whereas for streaming media, you do get poor performance, but it only happens after the buffer empties and you cause a glitch. So, this basically prevents, things like YouTube and things like that from being, classified as real-time applications, because, the end-to-end latency is an order of magnitude larger than the network latency. And RTC applications, of course, have been increasing rapidly in usage. And as of July 2012, Skype had 115 billion minutes per quarter, and out of that, roughly half is video conferencing, which is not just low latency, but also requires high bandwidth, because if you're doing like HD video conferencing, you want high throughput. And besides that, there's also increasing use of software applications, such as remote desktop. And this, of course, is becoming very useful because of Vdi Scenarios, which is essentially a virtual desktop infrastructure where you have lots of VMs running in the cloud, and people won't have machines sitting in their offices, right? And of course, applications like Office 365, where you're not necessarily streaming the whole VM, but you're essentially interacting with an application running in the cloud. And things like online multiplayer games, where lots of state needs to be sent across, so that you can have multiple parties playing. So, for non-RTC applications, only long-term average throughput matters. So for file download, it only matters like what the overall long-term average throughput is, which determines how long it's going to take to download the file. However, for RTC applications, since the end-to-end delay requirement is there, you can't use standard protocols like TCP for transporting the data. And the main reason essentially is two things. TCP relies solely on retransmissions for recovering from lost packets, and this adds to long delay. And the other reason is that TCP's congestion control essentially is going to build up long queues, and this causes additional queuing delay that's detrimental. So what I'm going to present today is essentially 3 technologies that we worked on to improve real-time interactive applications. And this is in the order they were kind of done. RAPID, it stands for Reliable Adaptive Protocol for Improving Delay. And this essentially is a hybrid forward error correction and ARQ protocol. So it relies on retransmissions, but in addition, proactively sends forward error correction packets to prevent retransmissions. And the second is, so this relates to like providing reliability for the application. The second is a universal rate control protocol, and this relates to replacing the congestion control portion of TCP. And this is a rate control framework which provides simultaneously low queuing delay and high throughput. And doing this simultaneously is very challenging over over noisy networks like cellular networks. And the third is PROTEUS, which is a work we just presented at Mobisys. And this is trying to predict what kind of queuing delay and loss rates you will see on cellular links, so that you can, the application can be more intelligent in how much error correction to insert, and things like how much, how long it should wait before declaring packets to be lost. So it relates to like de-jitter buffer sizes. So I'm just going to present, how an application, a real-time application kind of works. And this could be sort of like video conferencing or remote desktop type application. So the application generates packets which, it wants to send. They, let's say, go into some queue. And then this transmission strategy basically decides, I should send original packets or I should send forward error correction packets. And how much error correction to insert. And this portion decides what's the overall rate you can send. So this includes both the source rate and the forward error correction rate. So the first thing is, given, end-to-end route, what's the total bandwidth I can use? That's the job of this congestion control. And this guy's job essentially is, given this total rate, how I should partition it between forward error correction and original rate. And the application, of course, can then, using this knowledge, can decide what bit rate I should encode at, let's say for video conferencing, or let's say for remote desktop, it essentially can decide to lower the frame rate at which it's painting to the applications or updating the screen.
What exactly is the feedback going to the application rate control?
It can essentially be a combination of two things. One is it can be the total rate that the congestion control module is saying. So basically, it can be total rate and then the loss rate, something like that. Okay. Or in cases of remote desktop, it can just be, the buffer is kind of full, so back off on painting. So I mean, it essentially can be any knowledge such as like how full this buffer is, what rate is the buffer draining, and what kind of loss rate you're seeing. Okay.
You expect this to work on both TCP as well as UDP, or is this something?
So this can work on TCP also. The only difference in TCP is that you cannot be more aggressive than TCP, of course. So your transmission rate can be lower than what TCP tells you, but you can't make it, of course, higher than what TCP tells you. And the second difference is that in TCP, you don't have any control on how you recover from lost packets. So you cannot, there's no real advantage to doing FEC, right? But the URCP work, the rate control work, that can be applied to TCP as well.
So do you see a lot of RTC applications using UDP, or
yes.
Sort of because a lot of Skype that we see is TCP traffic.
So Skype actually should be mostly UDP traffic.
On cellular networks, it's TCP.
On cellular, it may be currently TCP, but for most other cases, it's UDP. And I think that in itself probably will change as time goes on, right? And actually, TCP is much worse on cellular links than what any UDP-based solution can be used. Okay. So first, I was just going to talk about the reliability portion, which is the hybrid FEC ARQ protocol. And this is explicitly designed for applications which require lossless in-order delivery, right? So this is like remote desktop. It requires lossless in-order delivery. And just because of this requirement, remote desktop was using TCP prior to Windows 8. Because they needed, TCP essentially gave them what they needed, except that it also gave them high delay. What we did was essentially for Windows 8, we developed a hybrid FEC ARQ protocol, and that is shipping as the RemoteFX for WAN solution in Windows 8. And so I can just firstly give brief introduction to FEC, very brief introduction to FEC. So forward error correction allows you to recover from lost packets without requiring retransmissions. So essentially you have, let's say, some certain number of packets, and you encode certain number of packets, and you add some redundancy, and then you can lose some of these packets. And if your code is optimal, then if you insert, let's say you have 4 source packets, you put 2 FEC packets, then you can lose any 2 out of those 6, and you can perfectly recover your data, right? And essentially, if you think of a block code, it's pretty simple. You can think of these as like, these are your original packets, and so you send your original packets. That's the identity matrix representing the original packets. And these can be sort of FEC packets, which are some linear combination. Let's say you lose these two, and then recovery is kind of easy. You just take the rows of the matrix corresponding to the packets you received. You do a simple matrix inversion, and you can recover, right? And the only difference is this is not, like actual integer math or anything. It's operating on fields. However, for remote desktop, you require lossless in-order delivery. So there's no point to using actually block codes, because in a block code, if you have block A, then block B, and so block B comes after block A, there's no point having FEC packets which just encompass block B, because block B by itself is useless unless you get the original block A. So instead what we use is we developed a sliding coding structure, which essentially operates like this. So let's say you send some packet, which is the first packet, then you send another packet. Now you can decide, I want to send some FEC packets. So you essentially, your FEC packet becomes a linear combination of everything that's in your queue. So you have these two packets. You have FEC packet 1, FEC packet 2. And now you decide to send a new original packet, right? And now if you decide to send an FEC packet, you kind of just keep growing your code. Does that kind of make sense? You essentially keep, basically the FEC code encompasses all packets that are in the unacknowledged queue, okay? So this is kind of like a sliding coding structure, which is not block-based.
So is there any proof of optimality or something? I mean, what is the claim we can make?
So this code is, it turns out there's no, you cannot make proof of optimality in the sense that, even if you have the sufficient number of packets, there may be cases where you cannot recover, okay? But empirically, we can show that, 99-point-some% of the times you can recover.
I guess if you have all the packets
yes.
Available to you and you did codes over that,
yes.
then it is optimal, right?
Yes, yes.
So you're trying to approximate that in some sense here.
Yes. So we're actually using what's called a Cauchy construction for codes, but we're essentially modifying that to a sliding block code. So it starts with, if it was a block code, it would be optimal. But since it's the sliding structure, you can't guarantee 100% optimality.
So just to,
yes.
I think I'm missing something here. So the purpose of the sliding code design is to ensure some form of in-order delivery.
Yes.
But is this always going to be in order, perfectly in order, or could it be just a little?
It will be. It will be in order. I mean, it will be in order if you have like a buffer, right? So you still may require a buffer for. So let's say like, here, let's say you lost 2 packets, right? Okay. Then, well, you have 2. But let's say you're up to here. Okay. You lost. Let's say you lose these 2 packets, okay? Then of course you cannot yet recover. You can only recover up to here, right? So what it guarantees is that unless you get an original packet, it will always be in order. So like if you're recovering from an FEC packet, the packet that you will recover will be up to all the packets up to the previous packet. So then I'm just going to talk about sort of an optimization for how you insert FEC. So let's say like this is a queue of packets. You have everything up to here. And in between here, you may have some, you may have lost some, right? These are kind of in flight, and you don't know. Okay? And then these are like new packets that are kind of waiting in the queue. Okay? So if you think about, what kind of choices you have, first thing you can do is you can just retransmit this packet, right? Because that's a valid thing to do. You can just say, okay, maybe this packet has been lost, I'll retransmit it. The other thing you can do is you can send an FEC packet, which encompasses, first and the second packet. The third thing you can do is you can take the first 3 packets. You can take the first 4 packets. Okay? You'll never just take these 2 packets, right? Because that, is not really the correct thing to do. Or you can send a new packet. So you have like a list of choices you can make, right? So how do we decide which of these choices to take? And that's kind of where we did this optimization framework where here this is let's say this x-axis is the index of the packet. This is the probability of what we call sequential decodability, which means this is the probability that I have all the packets up to, this packet J, okay? And this can only decrease because the probability that I have everything up to here has to be less than or equal to the probability that I have something up to here, right? And of course, it drops to 0 because there's no data sent here, right? So you can be 100% sure that nothing is there. So what you essentially do is like, if you send some FEC packet, what you do is you raise the probability of these in-flight packets, but you don't cause any change here, right? But if you send a new packet, then you don't change any of the probabilities here, but you kind of have some probability that you've gotten a new packet. And so you kind of do this analysis for all the potential cases, and that's kind of how we decide, which packet to send. And the details of how to compute this sequential decodability probability, that's kind of detail. So you're basically trying to optimize the expected sequential decodability delay for all the packets in the queue.
So the expected sequential decodability delay.
Yes. So each of these packets is going to have some sequential decodability delay.
So the first time at which everything
up to that point, yes, exactly. Right.
Right. And you're trying to minimize that.
Yes.
For which packet?
For all the packets that are unacknowledged or waiting in the queue.
So you take an expectation.
Yeah. And to do that expectation, you need these probabilities.
So you calculate the area under these curves and
Essentially, that's what it ends up being, yeah.
then find the one
Which gives you the maximum area, yeah.
By doing that, you might have increased the total number of packets, right?
Yeah,
Going across the wire.
sure.
So you have different FEC strategies, right? You could do the FEC and you just send the first packet or the first and second.
Yeah,
and so on.
right.
So that would result in a family of curves.
Yeah,
Yeah.
right.
And those will drop down to your blue curve at various points.
Yes, right. Yeah, exactly. So basically, if I just do a FEC packet up to here,
Yeah.
then I'll only increase up to here, and then the rest of it will kind of be.
Will you increase more than, I guess you will increase more than that orange curve there, right? In some sense. If you
Yeah.
The curve corresponding to doing an FEC on just the first 2 packets will be higher than that
It will be
orange
higher,
curve.
but then it will drop.
And then it will drop.
Yeah, but actually, there will be no discontinuity actually, because just by doing an FEC of these 2 packets, you still increase the sequential decodability probability of this packet as well, because maybe this packet is not sequentially decodable because it's waiting on something missing.
Okay, it will increase.
So it'll look something like this, where it will be higher up to here, and then it will cross over and be.
Cross over and
It will be
then-
smooth.
It will be smooth, yeah. The only discontinuity will occur here. Okay. So that's
So you have information about each packet in the sense that if this packet does decoding this packet requires
say, n number of previous packets?
So basically, the only information you have is that you know whether it's an original packet, or if it's an FEC packet, which packets it encompasses, right?
So, whatever is your strategy, it would be a static strategy for all. I mean, why would it change over time?
Why would it? Okay, so there's two reasons why it would change. One is that the actual loss probability is different. Okay, so for given loss probabilities, these curves would look different. The second is how many packets you have that are waiting in the queue, right? Because if you have lots of packets waiting in the queue, then there's no reason to. I mean, if you hold off, then all of them are going to be held. I mean, if you just keep sending FEC, then you're delaying all the packets that are sitting in the queue, right? So.
Well, I guess I'm confused about the time scale here. So
Uh-huh.
these orange packets have been sent.
Yes.
Not orange packets. Well,
The red ones?
the red ones.
The red ones, you know everything's up
You have
to.
some packets in flight, right?
Yes.
Don't you have to wait for sufficient time
Uh-huh.
for those to be acknowledged before even bothering?
So acknowledgements give you acknowledgements give you it changes the probability of a packet being lost or received, right? So when you send it, you have a certain loss probability. Let's say it's 2%, right? So you assume with 98% probability these packets will arrive at the other end, right?
No, but my question is about the time scale here. At what point? I mean, you talked about a decision process, right?
Yes.
At what point is that invoked? It doesn't make sense to invoke it too soon.
No, so what you do is you invoke it at every transmission opportunity.
Okay, so if it is very early, then you tend towards sending new packets.
If it's very early, then your expected probability that a packet has arrived is the estimated 1 minus the estimated loss probability. As time goes along, right? Then let's say you make
less confident that the packet made it through.
Exactly, right.
That every packet before, not just the packet.
So basically, after a certain amount of time, you decide, this packet has been lost, right? Then the probability that that packet made it through is 0. And then that updates all the probabilities in the...
So in principle, is it similar to network coding in some sense, coding for the same flow? Because you keep on sending until you get the entire, say,
Yeah, so network coding is pretty much FEC, right? It's similar, right? Network coding is essentially same concept, except in network coding you don't have a systematic portion. You essentially always just keep sending linear combinations, right? But the principle is the same. So I'll show a demo of the RemoteFX later.
Also, I imagine in some of these applications, after sufficient delay, it makes sense to just drop a packet. Is that something that?
Yeah, so this application is not one of them.
Okay, so your framework does not accommodate that. I see.
Right. So this kind of shows, this is the simulation essentially, but this essentially shows a CDF of the sequential decodability delay. And this is kind of an extreme case where you have 15% loss, but most of the time the loss rates are much lower. But this is kind of just to illustrate the gains you can get. So the red curve essentially is retransmission only. This green curve is opportunistic FEC, which means whenever the sending queue is empty, just send an FEC packet. Okay? This purple curve is FEC with the cost function invoked. So basically, trying to optimize when to send FEC packets. And this blue curve is essentially, prior knowledge. So I know which packets are going to be lost. I'm just going to send them always. And this essentially shows this, the sequential decodability delay, CDF. So with the optimization, it's kind of close to what prior knowledge would give you.
So So the blue curve is the round trip time, or the one-way delay divided by 1 minus the loss rate or something, is it?
Yeah, something like that. We'll try to approach that, yeah. So that's kind of on the rapid.
On the bandwidth side?
Okay. So the bandwidth side essentially is showing how close we can be to capacity. And so the way the simulation was done was we would send a burst of, we would assume the traffic is bursty. So every so often it would wake up and it would try to send a certain number of packets. And this essentially shows you, so what the decision essentially is doing is that how much of the burst actually can make it through. So this is the CDF of what percent, like, what's the bit rate that you can sustain. So next I was going to kind of switch to the other aspect of interactivity. So one was the reliability, and the other is the congestion control or rate control. So basically the motivation for this is that there's many networks where rate control strategies work well for interactive applications. So like Skype works pretty well if you use it over landlines, connected wired connections, but it doesn't work so well when you're doing it over, let's say, even Wi-Fi or 4G or WiMAX type things. And the main reason for this essentially turns out to be that these networks are kind of noisy. And what I mean by noisy networks is that if you consider a network and let's say you send at a very low rate, so you send packets at something that shouldn't be exceeding capacity, right? So like you're sending at 20 kilobits per second or 30 kilobits per second, right? And what you do is, let's say you look at the delay you get, which is essentially one-way delay or the RTT. And what you do is you plot the delay minus the minimum delay. So the minimum delay you assume to be sort of propagation, caused by propagation, and that's something you can't overcome. And you plot the distribution. So it turns out that for like cable modem type networks, this distribution is very narrow, meaning there's very little portion of delay that's not just propagation delay. Okay, but if you do look at the other networks like 4G or the WiMAX, then you see this distribution is very broad, right? So that's what I mean by noisy networks, which is that even in the presence of a traffic flow which is very low bandwidth and shouldn't be congesting the network, you're still seeing a high variability in delay. Okay? And this is kind of the same thing, but in a slightly more complicated format, which is what we did for this experiment was we essentially send at a particular rate for a certain duration of time, and then again just measure the delay, and we kind of plot the distribution along the y-axis. So the length of this bar is the minimum delay to the maximum delay you see when you're sending at that rate, and then we plot like 10th percentile, 50th percentile, 90th percentile, and mean. So that kind of makes sense how this plot is looking. So what you see is like, here you think, if we look at this kind of like visually, we can kind of see this looks like congestion, right? Because now we're consistently seeing high delay, right? But this stuff is kind of noise in the sense that, you're seeing a high range, this is a very broad distribution even when you're sending at low rates. And that's the same thing for the loss.
There's no particular pattern below the congestion.
There's no particular pattern, right?
So what are the spikes again? The blue spikes are what?
So this is the maximum delay you see. This is the minimum delay you see. So yeah, you see something like 5-second delay, which I think is pretty much what people report anyways.
So maximum delay.
So there was some packet, even when you're sending at 300 kbps.
That has no significance. It's a spurious thing. Isn't it?
Yeah, yeah.
It's only when the minimum also goes up that you
Right. Yeah.
This was on what?
This was on 3G. This is using a USB dongle.
On a mobile center.
It's a Verizon.
Is it moving or?
This is essentially not even moving, just it's sitting in one place.
Is the radiation reducing down to almost zero just before the congestion delay kicks in? Is that an artifact of the measurement, or do you think that's fundamental?
You're saying the variation reduced?
Around 600, the fact that
Just
everything-
below that.
Just before that.
Yeah, just below this. So wait, what was the
You're
question?
saying the tall vertical bars are gone, right, in that region.
Yeah, so
Just before that,
that's just a random artifact. Right. There's no reason why you shouldn't see tall bars even there. And we kind of do this for various networks, and this is WiMAX, and this was done like a couple of years back. So again, you can kind of see that that's congestion. And this is more recent. This is for 4G. In 4G, the distribution is still broad, but like the 90th percentile is much better, right? But the maximum is still pretty bad. And just for comparison, this is cable modem. So this is just to kind of show, here it's very nice. Okay.
can you just go back?
Yeah.
Graph on the left. So are you saying that's the point of congestion? Or what is the point of congestion?
Somewhere in between there.
The one-way delay is not increasing beyond that point because the queue is filled up, is it?
Where? Here the one-way delay is high, right?
Higher, but it is not increasing beyond that. It is still.
Yeah, that's the buffer size.
So the buffer is filled
Yeah,
up.
the buffer is filled up, right? But the loss rate's linear. Loss is linearly increasing. Okay, so that was kind of just like an overview of why. This kind of leads into why these types of networks are problematic for RTC applications. So RTC applications primarily use delay-based rate control. So if you look at Skype or Link or other interactive applications, they're using delay-based rate control. And since delay is a noisy signal, we can't make a good judgment as to when, if you're just looking at one delay signal, you can't make a good indication whether you're causing congestion or not causing congestion, right? And on clean networks, delay is clean. It allows for full link utilization. On noisy networks, it actually results in link underutilization, meaning you often confuse, you think you're congesting the link, so you reduce your rate, but you're not actually causing congestion. This is kind of just the random delay in the network. Loss-based protocols work better because loss is actually a cleaner signal usually. But we can't use loss-based congestion control for RTC applications because it always implies the buffer is full and the queuing delay is going to be high, right? And if you think of like the end-to-end delay that you see in, let's say, video conferencing, there's lots of components to delay, but the main one that's variable is the networking delay. So I just kind of break down the networking delay into different components. One is the propagation delay, right? This is just like a fixed value. The other is this delay noise, which kind of is what I plotted before, right? And the third is basically caused by queuing. So this is due to actual congestion, okay? And if you really want to achieve full link utilization, this component there has to be there in some capacity, okay? Okay. So basically, this is kind of shows that, you look at congestion signals, you adjust the rate. And so how do existing protocols perform on these types of networks. So here I have essentially these are loss-based rate control protocols. So this is, let's say, standard TCP, what you see in default Windows TCP. This is TFRC, which is meant for media applications, but in essence, it doesn't really do anything for video conferencing, because TFRC uses the exact same throughput equation as this guy. So essentially, if you look, the only thing it gives you is smoother rate, but it doesn't help you in terms of queuing delay. And these are, in pink, are the, let's say, delay-based that people actually use for video conferencing. So this is, let's say, this is Vegas, which is a delay-based rate control strategy. And this is Google's IETF submission, WebRTC. So there's an ongoing effort in the IETF to standardize real-time applications like video conferencing, and they even want to standardize the congestion control aspect of it. So if you look at the, so here's the average rate each of these achieves. So you see that and this is on the 4G upload direction, the T-Mobile network. So here you see like the throughput is pretty good for these networks, but the delay is very high, right, for these loss-based protocols. And if you look at these delay-based protocols, you see low delay, but the throughput is low, right? And so in essence, I mean, there's no existing protocol which gives you good high throughput and low latency for these types of noisy networks. And I'll just kind of give an intuition as to why this happened without going into too many details. So it turns out all rate control protocols have, in essence, what's an operating point. And this operating point is a function of protocol parameters and the final operating rate. And so it kind of looks like this. So here I have, let's say, delay. And let's say this is the PDF of the delay. This is the first plot I showed. And then let's say you have an operating delay point here. Okay? So if you do something like this is on the clean network, you actually get full link utilization. But if you have a noisy network and you're still trying to achieve this operating delay point here, then what's going to happen is the actual operating delay is much higher, right? Because just simply because of the distribution, and therefore you're going to confuse, noise in delay for congestion. And this actually gets worse as the noisier the network is. So you can actually, be far off. And why do you need a new protocol? The need for a new protocol essentially is that networks are not the same. So you want the same protocol to work on all kinds of networks, right? So here's a clean network, here's a noisy network. So let's say I just fix the protocol. I pick some protocol that works, which I think is going to work good. So it has some operating point here, right? This protocol is going to work good for network A, but for network B, it's going to give you link underutilization. And then if I change the protocol, let's say I move the operating point out, then you're going to see full link utilization on both the networks, but this network is going to see more delay than it needs to. You're going to incur higher queuing delay, right?
Maybe I should ask this earlier, but what exactly does inherent delay noise mean? Because some of this could be congestion because of other flows, right? Not your contribution, but other people dump traffic on the network that cause
right.
this to fill up. So, what is noise?
So noise is essentially short-term fluctuations in capacity. So it could be due to actual capacity changes, or there could be some flow entering or leaving, right? But what I mean by it's inherent delay noise essentially is the portion of noise that's caused by something that's not like it's not a competing flow actually, in the sense that it's not competing over a long time scale, right? So what we do essentially is, we start with essentially a utility maximization based rate control scheme, which uses delay as a congestion signal. But then the main contribution of URCP is that we essentially do a 3-stage adaptation. Okay, so this is kind of working. So you don't have to look at these equations in too much detail, but most rate control strategies just do this, which is you change the rate in response to congestion. So this delta here is your delay, and these two are sort of like parameters that you have, and this is your current rate. So if this guy is high, so delay is high, this becomes negative, so you're dropping your rate, right? So this is what most rate control protocols do, is just this portion, which is change the rate. The main difference between this and URCP is that in addition to just this rate adaptation, we also change these parameters in the rate control framework. So there's another adaptation which actually adjusts these to try to compensate for which network you're operating on. Okay, so if you're in a clean network, the operating point moves lower. If you're in a noisier network, the operating point moves higher.
So you need some recalibration or something. You have to know the
So you can either do some pre-calibration. So you can either probe the network when you start the flow, but then even after the initial probing, there is a background adaptation process which operates at a slower time scale to it continuously updates the parameters K0 and K2 also. So this kind of just shows on that same 4G network, we get the rate that we want, the higher throughput, but we get the delay levels of the delay-based protocols. Okay.
There's a recent NSDI paper from
the Sprout paper, yeah.
So
right.
How is that different from this?
So Sprout actually uses it's an available bandwidth estimation scheme. So it essentially has a model of the network. So it assumes that the network is modeled as basically the queue is modeled using a Poisson arrivals for the packets with a certain escape rate for the packets being dropped. And it essentially tries to use this network model to try to estimate, so like you're observing delay, like inter-arrival packet gaps, and you're trying to infer what state the network is in so that the observations match what the state you're estimating. So it's more like an available bandwidth estimation scheme. So there's two things. One is available bandwidth estimation schemes can't guarantee fairness, in the sense that the first guy comes in, he thinks the bandwidth is a certain amount, right? The second guy comes in and sees a much smaller segment of the pipe, and essentially the second guy will never be able to fairly compete with the first guy. And the second issue is that it's very specific to the network model. So if you can actually watch that talk on ResNet, Keith gave it to us.
Is it okay?
Yeah, yeah. So
I don't understand something here.
yes.
The basic problem you said was there was noise, the delay signal, right?
Mm-hmm.
Random spikes. How does adjusting the parameters the way you showed in the previous slide, how does that address that problem?
So what you do is you move the operating point out, so that essentially on a noisy network, you push the operating point further out so that you don't confuse delay noise for congestion. So you adjust the parameters.
Okay, where is the fact that this noise is inherently short term and not a sustained thing? Where is that being factored into the?
So that's kind of factored into the fact that the adaptations for the K0 and K2 are happening at a slower time scale than the adaptations.
Where is the time scale?
So the time scale is not explicitly shown here, but so these are the formulas for K0 and K2. They have these R max and R average. R average is actually the average rate in a 10-second sliding window. So that's where you're getting the different time scales. And same thing with delta average. It's the average delay in a 10-second sliding window.
So the instantaneous delay doesn't factor in at all.
Right. It doesn't factor in.
A lot of those spikes in that 10 second.
Yeah, the assumption is that if
you'll still get confused, right?
yeah, if you have a lot of spikes, you won't necessarily get confused. What will happen is you will keep pushing your operating point out until those spikes don't further increase the average delay. Okay. So that's where the time scale factors in. So that's the plot, and this is essentially just
Go back to
yeah.
The last one, the last row there, that is where K0 and K2 are fixed.
Yes, exactly. Right. Right.
How does this deal with fairness compared to Sprout?
So
Sprout cannot,
yes.
can be unfair.
Yes. So the way this deals with fairness is let's say you forget this, okay? If you fix K0 and K2, you're actually guaranteed fairness. And the reason for that is that every cycle of adaptation, the guy with the higher rate is going to decrease more. So the gap between the person with the lower rate and the higher rate keeps shrinking every adaptation cycle. That can be proved. That with fixed K0 and K2, it's going to be fair. With variable K0 and K2, the fairness relies on the fact that you essentially, it turns out like if you think of these, if you think of this delta average, in long term, delta average is going to approach delta, and R average is going to approach R. So the only thing that really matters in this is that every flow converges to the same value of these two parameters, R max and delta min. If they don't converge to the same values for these, then fairness is not guaranteed. But the way these parameters are actually updated, there's very high probability that you will, what this essentially is doing is that this is trying to figure out what is the estimate of the long-term capacity. Okay? So if every flow somehow can get the same estimate for long-term link capacity, and this essentially is the average background delay noise. Okay? And again, if all the flows can try to, if you can say that these two parameters are, all flows will get the same value for these two parameters, you can guarantee fairness.
So but that's when everybody is doing the same thing, right?
Exactly.
What if the rest are doing TCP and your
So there's a way for us to kind of figure out what's going to happen when you have TCP. Is TCP is going to cause more congestion, right? It's going to try to push the operating delay higher and higher, okay, until you see loss. So what's going to happen is that the way this K0 adaptation works is when this delta average increases, K0 increases, okay? And once K0 increases, actually this is flipped. This should be K2 and K0 should be on the inside. But once K0 increases, then you automatically push the operating point further and further out so that you can compete with TCP. And once TCP leaves, because of the way this beta is chosen, there's always a downward pressure to bring the operating point back to low levels.
So then it will become like TCP.
It become
like TCP if there are other TCP.
Yes, and that's
then
the
you won't
best.
get your delay benefits, right?
But you can't do that. You can't get delay benefits anyways.
But in cellular, you have queue separation anyway.
Right, so then the TCP won't affect you, right? It won't affect your delay or your... Right?
It still affect your delay because
But if there's
operator
different...
is servicing all the queues, but that's like a congestion delay, right? It'll
Right.
affect your delay.
Right, so then it's kind of like a single queue then again, right? Because if you're servicing all the queues, then if one of the queues is full,
You're doing round robin across queues.
I think it's kind of the same thing.
Effectively, like your queue is longer now because
Yeah.
in between your packets, there's a bunch of the other guy's packets that need to be serviced. So
It's like, it's kind of like a long...
5-4, right? It's not like your queue is filled up. It's not 5-4.
I think it would be...
wireless.
I think it will be similar in the sense that once your delay starts increasing, you will try to compete with TCP, right? Regardless of whether that happens with this multiple queue or the single queue, right? So this is kind of just the more results showing the overall CDF of delay. So this kind of just shows that URCP's delay profile, not just the average delay and the 90th percentile delay, but the entire distribution of delay is close to what delay-based protocols can give you. And this just shows you throughput versus time. So kind of just shows. And then regarding the fairness thing. So these are just, applied the algorithm to video conferencing, see how it performs. And basically what you're showing here is that, because of the decoder reconstruction logic, you have missing frames and you have different video coming out than the original. This is just one fairness result showing, you have flow 0 going from 0 to 900 seconds. Flow 1 comes in at 300 and leaves at 600. And we kind of show that they can fairly share the link. And I just show a demo of, so basically the rapid work, the initial FEC hybrid APC ARQ, that was incorporated into RemoteFX for WAN, which is essentially the protocol that remote desktop uses. And as of Windows 8, they're using this UDP-based protocol. And so they have the hybrid FEC ARQ, and they don't have the full implementation of URCP. That's being incorporated for Blue Plus One, so next year. But they have a pre-URCP implementation of delay-based rate control, and it's essentially a demo. They show that maybe I should launch it outside the PowerPoint. It's starting. And this is kind of from their advertising video, so I didn't make this video myself, but they're just showing the comparison between Windows 7 and Windows 8. This is like a transcontinental WAN, about 1.5 megabits per second, 200 millisecond OTT.
So they turn it on only for WAN, or is it always turned on, or selectively they decide when to turn it on?
It's only for WAN.
So somebody has to configure, or is it based on?
No, it's auto detect.
Based on 200 millisecond or some threshold?
Yeah, so I think what they do, do essentially is that they always initialize a TCP channel just for the connection. And then they open up a UDP channel in parallel. And then if the conditions like RTT and estimated bandwidth require it, they move, and they can move traffic to the UDP link. They will put all the traffic on the UDP link.
So the Windows 7 one is using TCP and that's
Yes.
UDP?
Yes.
Is there a way to see how much of the benefit is from all the
Networking stuff.
all the optimization you built into your
For the rapid.
as opposed to,
Yeah.
the fact that you're using UDP will give you some benefit, right?
Right. So I would have to instrument their code to get more information.
Do you have a sense from them of?
Yeah. So
They have TCP UDP results.
Comparison, right? I'm saying UDP we just use UDP and didn't do anything fancy like the rapid thing, you'll still see better results.
You'll still see better results. You're right.
Compared to
No, but they need reliability.
Yeah.
How do you do, you need
No,
reliable UDP, right?
so you could do FEC RQ, but without FEC optimization.
Okay,
So,
just FEC.
yeah.
So what happens if you lose things? It will not recover or what?
One RDP is designed to, I mean,
There are no iframe?
So I should clarify. RDP in Windows 7 requires perfect lossless transmission. As of Windows 8, they actually segment some of the regions. And so essentially they have three things open. One is TCP, one is UDP reliable, which is the 100% FEC plus ARQ. And then they have UDP unreliable, which is just FEC without the ARQ portion. So they have, and they can actually, once they do the segmentation, they can code some of the regions using 264 type video coding, and those they can code, well, they can send over the UDP unreliable. And so that's kind of the thing, and I think I'll just stop there. Yeah.
Any other questions? Okay, thanks, Ajit.
Okay.